Okay, thanks for the invitation to this wonderful workshop. Thank you to Hamza and the organizers. It's a pleasure to be here. Can everyone hear me well? Yeah, okay, cool. What I'm going to talk about today is work that I did mostly before I started at DeepMind. I moved to DeepMind just a few months back. I was working for Pacific Northwest National Laboratory for the US Department of Energy before that. Thinking a lot about problems that come up when you think about operating power grids with a large amount of renewable generation essentially dealing with all the uncertainty that comes from the unpredictability of solar and wind energy, and how do we account for that when we think about how to operate the power grid. So this talk is mainly about that, but towards the end of the talk I will allude to some applications of similar mathematical techniques that come up in AI and deep learning, which is the kind of focus that I have at DeepMind right now. I would like to acknowledge my collaborators on this work, Enrique Machada and John Simpson Porco, who are faculty at universities in the US and Canada. Okay, I'm just going to start the talk by giving you some background on the power grid just at a very high level. So the power grid has been undergoing significant changes in the last few years, and this is driven by a number of factors. One, as I mentioned, is the integration of larger amounts of weather-dependent renewable generation sources like solar energy or wind energy. And the most natural thing that these sources change is that rather than having something like a coal plant or a gas plant that you can dispatch by burning more or less fuel, you can control the amount of power that power plant produces. With these kinds of sources, although they're great and they're clean, sustainable and all those kinds of things, we can't control the weather, and so we don't know how much power we're going to get out of these sources, and we need to account for that uncertainty when we operate the grid. Another issue that's been happening is an increasing interdependence between multiple infrastructure networks. For example, if you think about the water distribution system or the gas distribution system, transportation and power, with the introduction of electric vehicles, there's an increasing interdependence between the electric system and the transportation system, or with the adoption of natural gas driven by fracking and lower gas prices in the US, there's been an increased coupling between the gas and the power grid. So this creates like coupling that you might not have accounted for when you traditionally operated the grid, and this is becoming increasingly important. Another change that actually will relate quite a bit to what I'm going to talk about today is this idea of having a smart grid, where the idea is that rather than having these large power plants that are producing power, you have something like the Internet of Things for the grid. So you have smart devices that are consuming energy and talking to each other and negotiating prices, and then somehow arriving at some automated mechanism for sharing power. And this is really the vision of the smart grid. And if we move to such a system, we will have to have a much higher degree of automation. We'll need to be able to compute things in a distributed way. We need to put intelligence on these endpoint devices. And so this creates additional challenges as well. Today's talk is going to focus on what's called the distribution system, which is like the last mile of the power grid, which you can think about the part of the grid that connects your local substation down to your home. And in fact, this is where a lot of the modern technology is being adopted. So for example, you can think of smart meters which record your power consumption and monitor things down at the distribution system much better. There's also an increasing penetration of active resources on the distribution system with the adoption of rooftop solar energy. So you can think about your home has a solar panel on the rooftop, and when you don't have that much of a local demand for electricity, you can sell back electricity to the grid, right? So because of all of these changes, the distribution system, which was actually quite dumb in the past without much active monitoring or control or estimation, this is with all of these changes, you need to change the way you operate the distribution system. Okay, and if you think about the mathematics of the power grid, you can write down what are called the power flow equations, which describe the steady state behavior of the grid. These equations are nonlinear, and if you think about the kinds of optimization problems that come up in the power grid, you get these very intriguing feasible sets. So you can get these non-convex shapes and disconnected feasible sets, and you need to deal with this kind of difficult geometric structure when you solve optimization problems on the power grid. And because of this nonlinear structure, you can actually get very strange phenomena. For example, you can get something called a loop flow, which means that if you have this kind of just simple loop network, even though there is no production or consumption of power in the grid, you can get solutions where there is power that's circulating, although there's nothing withdrawn or consumed. Of course, you might dismiss that as just a mathematical curiosity, but there is at least some anecdotal evidence that things like this happen at least around the Great Lakes in the US, where you have these long loops around the lakes. And this is typically a bad thing because it wastes power and it actually requires your transmission lines to have higher capacity. So this is something that you would want to detect and prevent if possible. People have done other kinds of analysis as well and shown that you can have cases where the grid only has unstable solutions. So although mathematically the steady state equations have a solution, if you look at the dynamics of the grid, none of these solutions would be stable. So if you start at one of those solutions and kick it away a little bit, it's actually not going to remain there, right? And you can also have multiple stable solutions. And this actually comes up a lot in distribution systems as you have these reverse power flows going back from your rooftop solar panels back towards the grid. You can get these systems which have multiple stable solutions and cycle between them. And this again is something that's quite undesirable because of various factors, and we want to detect and guard against these kinds of issues, right? So at the heart of all of this, it's basically calling for a need to understand the physics of the grid better and have computational tools that can do a rigorous analysis of the power flow equations, and that's exactly what we're shooting for in this talk. Okay, so the specific phenomenon that we will be studying is what's called voltage collapse. So if you think about a typical power grid and you look at the power consumed, or which is typically known as the load at any given node in the grid, and you look at the voltage at that node as a function of the load, as you increase the load you'll find that the voltage kind of tends to drop, and at some point beyond a critical value of the load there are actually no solutions, which means that actually physically what's happening is that the grid physics becomes chaotic at that point. And typically before that you would have two solutions. One of them is a high voltage solution with lower losses and stuff, and it's typically a desirable solution, and the other one is an undesirable solution. And so we want to detect how far we are from this point of voltage collapse, and also we want to detect if somehow we got stuck at this lower voltage branch of the power grid. So we want to make sure that we are operating ourselves in this high voltage branch, right? So we need analysis that tells us how to detect this, and this is really what we're trying to build towards, okay? And this comes up in a whole slew of operations, of activities that are done on the grid, and I don't want to go through all of these, but you can talk to me later if you're interested. Okay, so how are these equations solved as of now? They're typically solved using well-known numerical methods like Newton's method or Gauss-Seidel, and most of these methods, at least after careful tuning for these applications, tend to work quite well. Unfortunately, when they fail, it's difficult to diagnose why they failed, because Newton's method, for example, can be sensitive to initialization, it can be sensitive to numerical errors and conditioning issues. It can also fail if there is no solutions to those equations, right? So when these solvers fail, you don't know what happens, and typically grid operators have a bunch of heuristics to deal with these failure cases, and that introduces some level of conservatism into the grid operations. More recently, there's been a surge of interest in the controls and optimization communities trying to develop methods to solve these equations in a more rigorous fashion. So there's a bunch of approaches that try to pose the power flow equations as some kind of fixed point system and do fixed point iterations that are guaranteed to converge to the solution. There's also a lot of interest in using convex relaxations of the kind that Hamza was describing in the last talk, where you take these non-convex feasible spaces and relax them to something bigger and try to find a solution in this larger space and hope that you get lucky and find something inside. And there's also this interpretation of the power flow equations as the stationary points of what is called an energy function, and you can try to find power flow solutions by minimizing the energy function as well. So there's a bunch of interesting approaches in recent years that are developed for this problem. Unfortunately, all of these approaches either provide necessary or sufficient conditions for the existence. So it's still difficult to get tight conditions that are necessary and sufficient for the existence of power flow solutions. And that's really what we're trying to fix in this talk. Okay, so essentially in this talk we're going to look at distribution systems which are typically tree structured power grids. We're going to impose some constraints on them which I don't want to describe in too much detail, but suffices to say that those assumptions are typically quite valid in practice. And once we make those assumptions, we actually are able to develop a tight, necessary and sufficient condition for the existence of power flow solutions, right? So once you have those tight conditions, you can get visibility on the exact limits of the distribution system, so you know how much load your distribution system can take before things will go bad. We also provide a unified viewpoint on these various approaches to the power flow solution computation, and we show that all of these different approaches actually end up computing the same high voltage solution in this special case. Okay. So essentially what we're saying is that there's all of these three different classes of approaches, all of them actually find the same high voltage solution in this special case that we're talking about, right? So if a power flow solution exists, all of them will find it, otherwise they will fail and you can detect that they have failed, and that's an indication that there is actually voltage collapse and there are no longer any power flow solution. Okay, so any questions on that kind of broad picture of things and the contributions? Yeah.
So is it that you've sort of restricted the class of networks that you're looking at, and within that class, right, it's easy to solve, so any of these methods will work within that class?
Yeah, so it's basically what we were trying to understand is what cases of this problem do we have an exact analysis for, and the hope is that at least in some approximate form, that analysis will carry over to the more general case as well. Other questions? Okay, cool. So this slide is a little bit technical and heavy on notation. I wanted to have it to describe the physics of the grid. Unfortunately, some symbols are missing. I think some things got wiped out while I was exporting from PowerPoint. So we're going to look at power flow in tree structured networks. So we assume that we have a tree structured network, and each of the nodes in the network is a point at which power is consumed or generated. Each of the lines in the network is a wire in the power grid, and you can think of the arrows as just representing an arbitrary directionality to those wires, although that's kind of unimportant. The convention typically would be that this is like the substation in the grid, and then these leaves of the tree are actual individual consumers, so your home might be somewhere at the end, right? Okay. It's a shame that some of the symbols haven't appeared, but let's see. Okay, it works now. Okay, cool. So at each node in the grid, you have a quantity called the voltage phasor, which is a complex number that specifies the magnitude and phase of a sinusoidal voltage profile. So this is AC power flow that's happening, so all of the voltages and currents are all sinusoids, and you can represent that as a complex number. We're going to be interested in the magnitude, but it'll be convenient to work with the square of the magnitude, so we call this little v the square, and so we have a square root here. This theta is the phase of that complex number. So you can think of this as representing a sinusoidal wave with a magnitude of this and a phase shift of theta, right? Does that make sense? Okay, and then we have at the beginning of the tree, we have like a reference bus where the voltage is set to some arbitrary reference value. All of the other voltages are defined relative to that. And we have power flowing on each of these wires. So F from K to L denotes the power going from node K to node L. Okay? Okay, and you have this formula that expresses the power flow as a function of the voltages. We don't need to dig into it too much. We won't be using that. Okay, so the assumptions that were made here is that the network is lossless, which means that it doesn't have resistance, only inductance, or it has a constant ratio of resistance to inductance. And this constant ratio assumption is quite reasonable, because as long as all the wires in the grid are made of the same material, you would have the same ratio between the resistance and inductance everywhere. Okay, we don't consider what are called shunt elements, which are like capacitors that hang off of certain parts of the grid. For now, that's we can handle that, but for simplification, I'm going to ignore it for now. And we're going to assume that we're operating it in a balanced form, where like we operate the three phases of the grid in a way that there is a constant relationship between them. Okay, so subject to that notation, you can write down a simple set of conservation equations for the grid. So at each node, you look at the power injected or consumed. That has to equal the sum total of the powers flow going out from I to k. So that should be fairly natural. And because we are going to assume lossless and active power, you have the power flow going from I to k as just a negation of k to I. And then you have a reactive power balance. So because these are complex numbers, you have balance of both the real and imaginary parts. So the real part is called real power, and the imaginary part is called reactive power. And so the formula for reactive power is a little bit more complicated because you have to account for the losses. But the nice thing, and this is really the equation that's nonlinear, right? So this nonlinearity is what gives rise to all the non-convexity and all the phenomena that we talked about earlier. Because the network is a tree, you have n-1 edges and n nodes, so you can solve this linear system of equations explicitly for the flows as a function of the injections. So this equation in some sense you can eliminate by solving explicitly for the flows, and then you can plug that solution into this reactive power equation, and so then at the end you basically eliminated this linear equation and you just have one nonlinear equation per node in the network, right? So this is the system of equations that we're trying to analyze. So at each node we are writing down this reactive power balance, and we want to make sure that this is satisfied for all nodes in the network. Right? Okay, so if you stare at this a little bit, you might start to imagine ways to rewrite this in a way that it's more easy to solve. And we came up with 3 ways, all of which actually allow us to develop a different algorithm to solve the power flow equations. One way, which is actually inspired by the kinds of techniques that Hamza talked about in the last talk, is essentially to replace the equation with an inequality. And you can show that once you do this relaxation, this constraint is actually a convex constraint, and in fact you can rewrite it as a semi-definite constraint as well if you wanted to, based on the kinds of ideas that Hamza described. And so this kind of makes things quite nice, that rather than dealing with this non-convex nonlinear system of equations, you can deal with a convex system of inequalities. But of course then the question is, how do you go from the inequality to the equation, and that's something that I will describe on subsequent slides. The other idea is to rearrange some of the terms here. So you can essentially observe that there is this term that just depends on Vi, and the others depend on Vi and other V's. So you can essentially pull these terms to one side and rewrite this in this kind of fixed point style form. And this will give rise to an algorithm that just iterates this fixed point equation. So on the right side you have V, and on the left hand side you have some function of V, and you can just keep iterating this fixed point system and try to see if that will converge to a solution. And you can also observe that if you do a slight change of coordinates to the logarithm of V, you can write this as the stationary points of an energy function. So you can show that finding a solution to these equations is equivalent to finding a stationary point of what's called an energy function, right? So there's 3 different perspectives on the power flow equations, and what turns out to be nice in this case is that all of those will actually give you a way of solving the power flow equations with some guarantees. Okay, so let's think about the first approach with doing the convex relaxation. So here the idea is that, okay, I did a relaxation, but I want to somehow make sure that when I compute a solution to the relaxation, I will actually get equality here rather than inequality, right? That means that I would have solved those equations. So essentially the idea is to add an objective function that somehow forces these inequalities to become tight, right? And in this case you can see that each of these equations, it only has a positive dependence on Vi, and it has like a negative dependence on all the other voltages everywhere else, right? So if you have an objective that's an increasing function of your Vi, what this constraint is going to try to do is to allow Vi to become as large as possible, and because this part is growing linearly and this part is growing only as a square root, these V's will tend to become as high as possible and essentially only stop when you hit the constraint, right? Does everyone kind of see that? So essentially, because of the structure of the equations, as long as you have some kind of increasing function of V in the objective, you can make sure that when you solve this optimally, you will actually get a tight relaxation, right? And so, so you can actually solve this. It ends up being what's called a second order cone program, which is actually a special case of the semi-definite programs that Hamza was talking about. And this is not a new observation. People have looked at this kind of approach before, but we went ahead and analyzed it and showed that in this case you can actually prove that the relaxation is always tight, right? And the other nice thing about this is that the objective tries to find a high voltage solution. So it tries to maximize some scalar combination of the voltages, and this ends up being a very desirable thing in the grid, because you can show that this high voltage solution is the one which wastes the least amount of power, and in some sense it's the only stable solution in this case, and it has a lot of other nice properties, right? Okay, so this was the first perspective. How am I on time? When do I need to stop?
You're fine. You've got until 5:30 actually.
Okay, cool.
We're running slightly ahead.
So. Okay, cool. Okay, so the other perspective is using this fixed point rewrite of the power flow equation. So you can essentially rewrite this as V as some other function of V itself, and so if you abstract that in this vector form, you can rewrite it as your guess for what the voltages should be at time t plus 1 is going to be some function of your guess at time t, and you keep iterating until hopefully this will converge. So what you can show is that this function g that defines this fixed point iteration is actually monotone in V, because if you look at this part of the equation, all the dependence on V actually only involves positive terms, right? So if I increase the V's, this part of the equation is only going to go up, right? And there is a lot of nice mathematical theory that describes the behavior of these kinds of monotone functions. In particular, there's what's called the Noster-Tarski fixed point theorem, which says that if you look at a fixed point operator that is monotone, it actually has a unique maximal and minimal fixed point, and the maximal fixed point corresponds to this high voltage solution, which is exactly what we're interested in, right? So this gives you another perspective that says that, you know, I can view this as this kind of iterated application of this monotone map, and if I start at the appropriate point, I will keep increasing the voltages until I hit this high voltage solution, beyond which I cannot increase the voltages anymore. Yeah.
Yeah. Are these dynamics actually, do they correspond to things that actually happen in practice?
No, so this dynamics is not related to the dynamics of the power grid. The one that I'm going to talk about next is actually more close to that. Other questions? Okay, so essentially you can, so this, I mean, the dynamics is kind of fake here. We're just using it as a computational technique to compute these power flow solutions. And the last perspective is on interpreting this as an energy function. So you can actually write down an energy function which actually corresponds to the Hamiltonian of this dynamical system that describes the power grid. So I didn't talk about the dynamics of the grid so far, but there is a dynamics for which the steady state equations define the equilibria, and you can write down that dynamics as a Hamiltonian system with this as the energy function that drives that Hamiltonian system. And you can show that the solution of the power flow equations corresponds to taking stationary points of that energy function, right? So this is really nice. So you can rewrite the problem of computing power flow solutions as finding stationary points. The problem with this is, of course, that this energy function is not globally convex, because you actually do have multiple solutions to the power flow equations. So there's multiple disconnected stationary points. But you can prove that it's actually convex over a limited domain. So there is an interesting domain of like desirable power flow solutions which correspond to these kinds of high voltage style solutions, over which this energy function actually is convex. And so you can again find the stationary point by solving a convex optimization problem. So rather than minimizing the energy function over all of Rn, you're going to minimize it over the subset over which the energy function is convex, and you can prove that it will still find this stable solution. Okay, so essentially what I've told you is that you have this monotonicity approach with the fixed point iterations, you have this energy function approach, and you have this convex relaxation approach. And in fact, each of these approaches allows us to establish a separate property of the power flow solution. So based on the convex relaxation, we can actually establish existence and uniqueness. So if the convex relaxation actually was infeasible, so you could not find any feasible solution to the convex relaxation, that means that there were no power flow solutions to begin with. That means that you actually hit this voltage collapse point. And if that if the convex relaxation was feasible and you solved that optimization problem, you will actually find this unique high voltage solution. Similarly, because of this monotone fixed point iteration property, you can establish the monotonicity of the voltages with respect to the power consumption. So you can prove that if you increase what's called the reactive power injection at all the nodes in the network, the voltages can only go up, right? And this is actually quite important, because in the actual grid they have this control mechanism that tries to keep the voltages constant, and the way it does this is that there is a decentralized controller at every point that detects if the voltage goes below some point, you inject more reactive power using a capacitor or something. And this monotonicity property tells you that that actually is the right thing to do, because it shows that as you increase the reactive power, the voltages can only go up. So in some sense it proves that those kinds of controllers are doing something sensible. The energy function minimization viewpoint tells you that you're actually at this bowl of the energy function, which actually characterizes the physics of your grid, and in fact, because you're in this convex part of that bowl, you know that you're at a point that looks like this, and if you perturb the point a little bit, the physics of the grid will try to take you downhill here. So that proves that actually you're stable, right? So in some sense, by looking at these different viewpoints on the power flow equations, we get different properties of the power flow solution. And in this special case, it's quite interesting that there is this one special solution that has all of these desirable properties that we would want to have, right? So this is the formal theorem. Again, I'll probably gloss over it a little bit, but just to kind of outline the logic of how this works. So if you assume that a power flow solution exists, then using this monotone interpretation of the power flow equations, you can show that there's a Noster-Tarski theorem application that shows you that there exists this unique high voltage solution, and the fixed point approach will succeed. And because of this monotonicity property established here, you can show that the convex relaxation approach will succeed, because you know that as you increase the voltages, that left hand side of that relaxation can only go up. And based on this, if you write down the conditions for optimality of that convex relaxation, you can get some analysis that tells you that at the optimal solution you will be at a point such that the energy function is convex. So you can prove that the Hessian of the energy function will be positive definite at the point where the convex relaxation succeeds. So in some sense, it would have been difficult for us to establish these results by looking at only one of these approaches for solving the equations. By looking at all of them together, we actually are able to somehow bring together these different mathematical tools and establish very strong results, right? So I think this is a nice example of different kinds of mathematical tools coming together to help you establish this. Any questions on this? I know that I didn't give all the details, but anything that's particularly confusing? Okay, cool. And all of them, in fact, will find the same high voltage solution as I described. And you can also show that this high voltage solution is somehow a smooth function of all the parameters of the problem, right? So you can prove that you can define this high voltage solution as a mapping from the space of injections to the space of voltages, and that mapping is well defined on a set that is known to be convex, and on that convex set this mapping is continuous. If the injections don't belong to that set, then no power flow solution exists, and this power flow solution is such that component wise, so the voltage at any node in that solution is higher than the voltage at any other solution of the power flow equations for that same vector of injections, right? And it's stable, so if you look at the Hessian of the energy or the Jacobian of the power flow equations, it actually is going to be positive definite, and that you have this monotonicity with respect to reactive power. So if you push more reactive power into the system, the voltages can only go up, right? So in some sense, this is like a complete characterization of the power flow solution space. It allows you to deal with detecting when you have voltage collapse, detecting when you might be at an undesirable power flow solution, all of the kinds of issues that I talked about in the beginning of the talk. In some sense, you have a complete resolution with this approach, of course under the assumptions that we made. Okay, so again, just kind of reiterating this picture and reiterating that, like, in some sense, like, this was nice for me that there's all of these different mathematical viewpoints that contribute something to this analysis, and I think it's a nice example of, like, the power of these different mathematical tools. Okay, so I moved a few months back to Google DeepMind, and I started thinking a lot more about artificial set systems of equations that come up in what is called deep learning. So we're typically interested in some kind of classification task. For example, you want to take images and predict a label that says what that image looks like. So for example, you want to take this image and say that it's a panda. At DeepMind and various other places, people have achieved a lot of success in building these artificial neural networks that map from these high dimensional inputs to labels. So you can think of these neural networks as essentially just implementing a simple transformation at each neuron and then passing something forward to each layer. There are some analogs with how the brain works, but of course to be taken with a pinch of salt. But the important and interesting thing is that people have achieved state-of-the-art results with applying these kinds of techniques to various classification problems. So there's this very well-known classification task on what's called the ImageNet problem. I think it has like several hundreds of thousands of images and a few thousand categories, and to date the state-of-the-art results for these kinds of problems are achieved using deep learning and neural networks. Of course, all of this is great, and this is why this field has seen so much interest from Google and Facebook and all these companies. But at the same time, these methods are rather black box. So even though you're able to train these neural networks to do these prediction tasks, you don't understand what's happening inside, right? So most of the people, even who actually work on designing these neural networks, it's very difficult for them to tell you exactly what component of the image is being processed and at every neuron here, right? And this lack of understanding has given rise to a lot of fragility. So people have shown that you can actually very easily fool these neural networks. So this is kind of a cute example where you take this panda and you add a very small amount of what looks almost like random noise, and it fools the network into thinking that it's actually a gibbon instead of being a panda, right? So these methods, while they are very powerful in terms of being able to learn complex relationships, it's very difficult to reason about exactly what they're learning, and this makes it very fragile to these kinds of attacks, right? And so the question is, once you have trained such a network, can you check whether it might be susceptible to things like this, and can you use that analysis to somehow improve the network and make it more robust to these kinds of phenomena? And in some sense, like, that corresponds to something, a problem that looks quite similar to the problem that I talked about. You want to make sure that there is no perturbation y of the input to your neural network such that the output changes with the perturbation size being controlled, right? So this tells you that if you were at an image that was definitely a panda, you could not perturb the image by a small amount and fool the neural network into thinking that it was something different, right? So this is what's called adversarial robustness in neural networks. And you could think about essentially trying to do some analysis of a similar kind to analyze the structure of solutions to these equations and trying to see what you get out of that. So I think this is a very exciting topic, given that a lot of these technologies are being deployed in various applications, including in things which are critical like self-driving cars. And so it's very important to make sure that these things will do the right thing under all kinds of situations. So I won't say too much more about this. There's a very active area of research, but I'd encourage you to think about these kinds of problems, and if you have any further questions or want more information, feel free to talk to me offline. So I'll conclude there. The paper that I talked about mainly has been published at IEEE Control System Letters. You can find it on my webpage, and that's my email. So feel free to reach out if there's something you'd like to chat about. Yep. Thanks.
We have sort of 5 minutes or so for questions.
Yep.
If you can talk about it in the last equation that you showed.
Yeah.
Do you want that to hold for all x or?
Right. So there's 2 versions of this. The one version is that you can ask it to hold for all x in your training data, which makes sure that at least you're robust to adversarial examples in your training data. The other option is to say that I have some bounds on my inputs. So for example, I know that, I don't know, I have a self-driving system, and I know that one of the inputs is the acceleration of the car or something, and I know that there's some bounds on that, or like the voltage in the power grid or something, right? So you may have bounds on x, and you can ask that this property holds for all values of x within certain bounds.
Doesn't
Right.
that mean that the function will be constant?
Right. So you would have to change the formulation a bit to say that it doesn't change by more than some amount. But that kind of, very simplistic formulation may not be the right approach for like high-dimensional statistical systems. So another approach is to try and build a model of what x's are reasonable, so some kind of generative model of the x's, and then given that kind of generative model, you can ask the same question, that if there's x's that are likely under your generative model, can you prove that for those x's this would be true? Yeah. But yeah, even how to formulate this question correctly, it's a big area of research. Yeah.
So in the power grid discussion, you said that the proofs you've made made a number of assumptions, one of which was to do with loss, no loss.
Yeah, so the losses actually, so yeah, one version of the assumption says that you don't have any losses, but I think the more realistic assumption, which actually also suffices, is to say that all the wires are made of the same material, which means that they will have the same ratio between resistance and inductance. So in that case, you will have losses, but there is a mathematical trick that allows you to transform it such that it looks like a system with no losses in some transform coordinates.
For a heterogeneous sort of network, you might that constant ratio might not hold.
Yes. So for example, like if the material that makes up your wires is different in different parts, then definitely will not hold. So it's not, I would not say that it holds all the time, but I think in particular for distribution systems, it's a reasonable assumption on average. Yeah.
So you have a feel for how stable your results are for that more heterogeneous.
Right. So definitely these results show that the solutions are actually smooth as a function of the parameters of the problem. So you could imagine that if there's an epsilon perturbation, like these results will not change drastically. Of course, as those perturbations get bigger and bigger, at some point you can see cases where these kinds of phenomena will not be valid. But I think what is still true is that there is kind of this fairly big operating space of the grid where there is this special solution that has all the desirable properties, and in some sense you want to characterize that space as well as possible and make sure that you don't go outside it. So I think that intuition still carries over. Yeah.
So in the power flow example, are the 3 algorithms then equivalent? I mean,
I'm sorry?
the 3 algorithms, I mean the 3 approaches, they're all equivalent?
They are not equivalent in the sense that if you look at them as iterative algorithms that find the solution iteratively, the iterates they produce will be distinct. But at the end, they will all converge to the same solution if one exists. Yeah. Other questions?
Did I understand correctly that there's some sort of library of test examples that people use for image analysis?
Yes, so there are several such libraries. I can point you to and all of them are actually publicly available now. So yeah.
on the
Yeah.
power flow example, which I found very interesting, and
Yeah.
it's sort of often with real world applications, you end up in a situation where you borrow various techniques and try and blend them
Yeah.
to solve something that doesn't quite fit.
Yeah.
But I mean, by the end of it, I had the impression that this was maybe a bit more general than about power flow. You didn't have particularly strong assumptions that you were. I mean, there was the monotonicity aspect, but I mean, is it actually more of a general approach than just power flow? Did you think?
Yeah. So I've seen each of these tools being applied to different sorts of systems. So, for example, I think the monotonicity has been used a lot in I think biological circuits and stuff, where you know that certain the physics dictates that certain things will only increase. The thing that I haven't seen is this kind of example of like multiple approaches kind of leading to the same solution. That somehow seems to be a bit special to this application, but each of those techniques in some sense is quite general and has been applied to several different things. For example, the convex relaxation has been applied to various applications, like Hamza was talking about. This idea of monotonicity has been applied to various kinds of systems. Of course, even this idea of energy functions comes from physics, and it applies to a lot of different systems.
So my question
Yeah.
was really if the blend itself was more general than maybe not that you haven't seen.
Perhaps. I haven't seen such a blend, but it would be interesting to think about what's the most general system of equations for which this kind of analysis will give you something. Yeah, it's a very interesting question. Yeah.
Could you also apply this to the transmission grid? Because there it's not a tree, but you actually have multiple pathways between the different.
Yeah, so for a transmission grid, actually things become a lot trickier because we were using the specific structure of the tree network to simplify things here. For a transmission grid, you can get all of these, like the loop flow kind of phenomena that I was talking about. And in general, it's known that you can have cases where like there's only unstable solutions and these kinds of things. And so I'd be very surprised if something like the results that we had holds. But I think, as I was explaining to the other person also, that I think the intuition that there is a set of desirable power flow solutions that if you could characterize that, you would be in business. I think that holds. But the tricky thing is how would you characterize that space of desirable solutions and make sure that you remain within that set. Other questions?
Could I ask a
Yeah.
question about, you just used the term in business.
Yeah.
Is this business designing a network, or is it in the minute-by-minute management of the network?
This is more in minute-by-minute management. So essentially what we're developing is tools that give you visibility into how far you might be from a potentially dangerous situation on the grid. And so in some sense it's used for what's called contingency analysis on the grid or security estimation, those kinds of ideas. Other questions?
All right, then, in that case, let's say thank you to Krishnamurthy and also Hamza as well for two very interesting talks.